Give a little bit, give a little bit of my time for you. Give a little bit, give a little bit of your time for me. There's so much that we need to share, so take some time and show you care. Hey, welcome to this week's installment of video notes from Mr. Fluids Physical Science class. Today we're going to be talking about fluid principles and gas laws, alright? Hey, these notes, you guys, will go on page 15 in your science notebook, alright? Let's go ahead and get started. Alright, so the first thing we need to talk about is fluids, okay? So you can see here that fluids can be anything that can take on any shape and can flow. So that includes liquids and gases, as well as if you want to put on there plasmas. But in this case, we're really just going to focus on liquids and gases. Alright, so our first fluid principle is Pascal's principle. Alright, this has to do with hydraulics. Alright, and it kind of says this: if you apply pressure to one part of a fluid, that same pressure is transferred throughout the entire fluid. Alright, so we can apply this to things like toothpaste tubes or mustard bottles, and also things that are important, even more complex, like jacks or tractors or car brakes. Okay, and basically it kind of comes down to this, right? If I take a tube of toothpaste and I squeeze one end, that force is transferred all the way through the toothpaste to the nozzle where the toothpaste will come out. Alright, so next one we've got is Bernoulli's principle. This is our second fluid principle. Alright, that's how you say that, Bernoulli. Alright, and he kind of said this: the faster a fluid flows, the lower the pressure. So it's like this opposite relationship, right? So the application of this is kind of explaining how aircraft fly, right? This applies to helicopters and hang gliders and birds as well. Alright, the airflow over the wing causes flight to happen. Let's check out how that works. Okay, so I want you to draw this picture with me, okay? We're going to draw an airplane wing. We're going to look at it like if we sliced it like a piece of bread and looked at it. So it's kind of got a rounded front edge, and then it trails off at the back to a much narrower point, like so. Excuse the little gap there. Alright, now as air flows over this wing, it flows in a particular way. Alright, when the air comes to the front of the wing, it has two choices. It can go over the top, or it can go underneath. Alright, now as it does this, the air that goes over the top gets accelerated because it has a longer distance to go, and the wings move it at a constant speed. So on top, we have faster air. Now Bernoulli's principle says that the faster a fluid flows, the lower the pressure. So because we have faster air, we have low pressure. Okay, on the bottom of the wing, we have slower air. The air doesn't have to accelerate to catch up. So that means we have higher pressure. This is what causes lift on a wing and allows airplanes to fly. Of course, that wing needs to be moving fast enough to create a big enough pressure difference between the top, where there's low pressure, and the bottom, where there's higher pressure, in order to get that airplane to stay in the air. Now, I've used this word a few times now, pressure, right? And we're talking about Bernoulli's principle. Well, what pressure is about force per unit area, right? So a lot of times when we're talking about pressure, and we're talking in our measurement system, we're talking about pounds per square inch. So that kind of means this, right? if you've got a square inch, approximately like that, how many pounds are pushing on it? Well, in metric system, we're going to use pascals, okay, which is PA. Or because pascals are such a small unit of measure, we're going to use kPa, or kilopascals. All right. Now, when we talk about air pressure, okay, like on a wing of an airplane or on the inside of a container, air pressure is the result of air particles bouncing and hitting off the surface of an object. Remember, when air particles are moving, they are bouncing all over the place, and when they hit an object, that exerts force and causes pressure. All right, so we're moving on to the gas laws. All right, and the first gas law we're going to talk about is this one right here, Boyle's Law. That's how you say it, Boyle's Law. That was the guy's name. Okay, and it basically says this, right? When pressure goes up, the volume of gas will go down. Okay, and it has a little equation with it there. P1V1 equals P2V2. All right, P stands for pressure, which is in kilopascals, and the volume is always in liters. Make sure you have that equation down because we'll be using it in class. All right, now here's the other gas law that we have. This is called Charles' Law, or as I affectionately call it, Chuck's Law. Okay, and it basically says this, right? When the temperature of a gas goes up, the volume of that gas will also go up. All right, that has an equation with it, right? V1 over T1 equals V2 over T2. So different equations for different laws, right? It has to be that way because this isn't an opposites law like Boyle's, right? This is the same. When one goes up, the other tends to go up too. Now here's something really important. The temperature that we use has to be in kelvins. Okay? And I'll explain to you what kelvins are here in just a moment. All right, so the Kelvin scale is based on an idea of absolute zero. All right, make sure you write this down. So absolute zero is that theoretical temperature when everything stops moving. Okay, up until then, there's at least a little bit of motion. So absolute zero is 0 Kelvin, or negative 273 degrees Celsius. Okay, now to this point, we've never cooled anything down to absolute zero, so we don't know what will happen, but we've gotten close. Converting things in the Kelvin scale is really, really easy. All you have to do is take Celsius and add 273 to it, okay, to find Kelvin. All right, so the temperature in kelvins is just Celsius plus 273. So if I have 30 degrees Celsius, that is 303 Kelvin, right? Negative 4 degrees Celsius, that is 269 Kelvin, okay? What would 100 degrees Celsius be? Think about that one for a sec. You should find the answer really easily. Thanks for tuning in, folks. We'll be talking about all this stuff and doing demonstrations in class, but I'm really glad you tuned in so you have the background information in your notes. Well, I hope you have a great day, and we'll see you in class. Bye-bye.